Okay, good evening, students. Are you ready for the presentation? I think you should be ready. 자, 오늘 지금 들어오신 분은 그룹 넘버가 어떻게 될까요?
질조입니다.
1조. 오케이. Okay, good evening, students. Are you ready for the presentation? I think. 예, 유튜브로 나가는 게 지금 조금 딜레이가 생기죠. 레이턴시가 있어요. 예, 잠깐요. 예, 자, 준비가 되셨을까요? 혹시 오늘 발표에 나름대로 오거나이저 역할을 누가 하실까요? Who is the organizer of today's presentation? 예은비?
네, 교수님.
오늘 은비가 전체 총대를 메야 되나?
다른 분이
누군데?
네.
누굴까요? 예, 일단은 비디오를 다 좀 켜주세요. 예. 그러면 얘기를 아직 그럼 안 한 거야? 그러면, 지금 현재 4명, 5명인가요? 민석이까지? Jerica, who are the members of this group?
Just 이예운 D and then
카메라 켜져 있는 네 분이 저희 멤버 맞습니다. 그래서
아까
예,
그러면
은비.
오케이.
오규총, 이송민, 이송원.
Okay.
They are all here already, Professor.
Okay, good. There were 5 before, so that's why I asked. Okay, so who are in charge of, who are, let's say, organizing today's presentation? 없어요? 그러면 은비가 총대를 메고 갑시다. 자, 시작해 주세요. So your group number is 7, right?
Yes, Professor.
Okay. Again, I started to live stream our presentation on YouTube. So the URL for the live stream of the YouTube is posted on the open KakaoTalk room. So you can spread to whatever. You can toss it to whoever you like to share. Okay. All right, go ahead. 자, 지금이 7시 1분입니다. 7시 15분까지, 16분까지
교수님.
맞추도록. 예.
화면 공유가 막혀 있습니다.
오케이. 해줄게요. 네, 이제 가능하죠?
네, 잘 보이십니까?
네, 잘 보입니다. 시작해 주세요.
Hello everyone.
My name is Seungwon Lee. Today, our group is going to present how we conducted the Rockwell test and how the result came out. Our group member is Thank you for participating with us, and I'll start begin presentation. Next. This is today's content. Next. The purpose of this experiment is to measure the Rockwell resonance. And by doing this experiment, we can measure the speed of shear wave and rod wave. Next. This picture is the finite element model of the specimen. The original way to analyze shear wave and bending is complex. However, by using OSR method, we can easily identify the shear waves. The blue points of specimen is called nodal points. At this point, it has no effect of bending wave, thus we can analyze only the shear wave. Next. By comparing these two figures, we can identify the characteristic of nodal points. The first graph shows the bending wave along with the shear wave. The second graph shows the shear wave with minimal bending. Next. By following equations, we can calculate the modulus of elasticity and shear modulus. And by these two numbers, we can also calculate the Poisson's ratio. By Rockwell test, we can do ground seismic analysis and we can check the maintenance of structures. Thank you for listening, and next presenter will be Lee Seung-min.
잘 들리시나요?
Okay, go ahead.
Hello, my name is Seung-min Lee, and I will talk about equipment and process. 넘겨주실래요? This is equipment of this experiment. 넘겨주실래요? For the first one, dynamic signal analyzer, this helps us to see the result of the test. 넘겨주실래요? This is accelerometer. This helps us to see the result of the wave. 넘겨주실래요? This is cable. This helps us to connect the specimens with the machine. 넘겨주실래요? This is specimens with basic information. As you can see, the bottom part of the specimens, the basic informations. 넘겨주실래요? Another specimens. And this is impact hammer. This helps us to make clear hit when we do the test. Then the next chapter is process. I consist this with 8 chapters. First, enter the given value of the basic settings to dynamic signal analyzer. Then attaching cable to lock and machine. And then press the start button and hitting the sample with a hammer. Then press end button after the test. Then select the measured value of the load wave test. We have to select the peak value of the test. Then circulate Poisson's ratio with program. Then save data of the test. Then repeating process 1 to 6 for shear wave test. Then repeating process for each sample. Then the experiment is over. 넘겨주실래요? For more explanation, when we attach cable to specimens, attaching on top of it for load wave test, then on the side of it for shear wave test. 넘겨주실래요? Hitting sample with a hammer. When we do the load wave test, we attach cable on the top part, and we have to hit the opposite part, the bottom part of it. 넘겨주실래요? For shear wave test, have to hit the pointed part vertically from the surface of the sample. Especially the distance between the bottom part and the hit point must be the same distance between cable attached part on the side part and the top part of the sample. This is end of my part. Thank you for listening.
Hello, good evening. I'm the third presenter, Yembi, who will talk about the result of tests. These are the load and shear wave graph of aluminum and granite 1, 2, 3. You can have load and shear frequency and also Poisson's ratio in this result. But load and shear wave frequency, we can also calculate Poisson's ratio and P wave. The length of aluminum is 10 centimeter and the weight is 545.45 gram. And weight is 514. And the length of granite 2 is 15 centimeter and 842.3 gram. Of granite 3 is 20 centimeter and the weight is 1,177 gram. You can get density with this measurement and load or shear wave velocity with frequency. In this result, Vc is meter per sec and always bigger than Vs. And granite 2's Vc and Vs is the highest, and the lowest Vc is for granite 1, and the lowest Vs is for granite 3. Then with density Vc and Vs, we can get Young's modulus E and shear modulus G in Pascal. Because Vc is bigger than Vs, of course, the Young's modulus E is bigger than shear modulus G. Likewise, granite 2's E and G is the highest. Finally, Poisson's ratio of aluminum is 0.35, and granite 2 is 0.21, and the granite 3 is 1.97. Thank you.
Hello, my name is Gyu Jong-ho and I will give a presentation on the analysis and discussion part. Next. Generally, the pressure wave velocity is larger than the load wave velocity, and the load wave velocity is larger than the shear wave velocity. In our test, the velocity values were appropriate for aluminum and granite 2. However, in granite 1 and granite 3, the largest value was obtained in the load wave velocity. So in granite 1 and granite 3, the Poisson's ratio is also poor. This table summarizes the Poisson's ratio we obtained. The normal Poisson's ratio of aluminum is 0.35, and the normal Poisson's ratio of granite is 0.2 to 0.3. In our test, the Poisson's ratio of aluminum was 0.35 and that of granite 2 was 0.21. And the Poisson's ratio of granite 1 is 1.12 and that of granite 3 was 1.97. Therefore, next. Therefore, we can see that the tests with aluminum and granite 2 were quite successful, but the tests with granite 1 and granite 3 were not done accurately. Next. There are several reasons why the test was not accurate. First, multiple strike might have been applied instead of a single strike in a short time. And fissures and cracks in the specimen are not verified. And the specimen was in contact with the desk and might have caused the wave to spread to the desk. and any vibrating object on the desk might affect the test, and bonding between specimen and accelerometer may be poor. If the test had been conducted by supplementing these points, more accurate values would have been obtained. Next. Lastly, we would like to thank Professor Joe for giving us this opportunity to give a presentation. Thank you for listening.
Okay. All right. I appreciate your efforts and work on the presentation from the resonance test on the rock horse. Generally, it was done pretty well, but I think there must be some additional discussion, and then some concerns should be expressed in terms of the result. Okay, let me go to each individual quickly. Hopefully, you guys are answering my question with let's say with a good support. Okay, first of all, I think our the presentation and discussions are watched by somebody else's over the world, hopefully, and so we have to utilize English throughout, so no Koreans are allowed. Okay, all right. First of all, in case of Seungwon, I'm kind of worried if you are understanding the shear wave measurements. So in other words, the principles of measuring the propagated shear waves. And then, so in terms of guideline of a good measurement, kind of comfy, I mean, the whatever, a reliable measurement of the shear wave propagations, torsional shear waves, of course. I ask you guys to use OSR technique, optimized shear wave resonance technique. So Seungwon is trying to explain what it should be, and then but his explanation was not so clear, and then I like to make sure because he is in charge of explaining the theory. So I like to make sure Seungwon has a good understanding and then capability to explain that to others. Okay, so in that regard, Seungwon, can you explain it or summarize the theory of OSR quickly, and then what kind of waves to measure in this resonance test?
But I have understood that there is a nodal point in the specimen, and in that nodal point, effect of bending. So we can the results of
What is the definition of nodal points that you are using right here again?
At nodal point, we can calculate the shear wave.
Okay, looks like you don't have quite good understanding on it, and then because we don't have enough time, and then we have to finish everything in 3 or 4 minutes. So let me move to Seungmin, and in the middle of the presentation, looks like you showed kind of typical image of accelerometer. Is that right?
Sorry, I don't understand where. Can you explain again, please?
So I don't know the number of pages from your presentation.
Yes.
And then looks like there was a picture
Yes.
of small cube with the gray color, but to me it looks like accelerometer. Is that right?
Oh, you mean that the picture of the picture when I explained the equipment, there was a accelerometer and the small cubics on the maybe the left side are
Yeah, that's right. That's what I'm saying. Yeah, but actually, it is MEMS, I think, MEMS, and that's a totally different type. Of course, it is an accelerometer, but you know the accelerometer that you used for this test. I was wondering why you showed it, which is totally different from what we used, and I couldn't understand.
That's I prepared this picture because I don't know where about the accelerometer. I am sorry about that, but but the as you know the in the picture on the right side the total machine can't explain about the accelerometer, so I get picture from internet.
Okay, so let's say here we used two different types of waves
Yes.
for the resonance measurements. The first one is rod wave measurement, and the second is shear wave measurements. So depending on the type of the waves, you place the accelerometer at two different locations, right? And the
Yes.
first one for rod wave measurements, you placed the accelerometer at both ends. I mean, at one of those the core ends. So you attach the accelerometer vertically to the perpendicular to the side of the core. And then in case of shear wave measurements, you attach the accelerometer probably 2 centimeter away from the end of the specimen, and then the location, the direction of the accelerometer is like a parallel to perpendicular. It's kind of ugly to explain, but it's like maybe I may have to say parallel to the axis of the whatever the specimen, right? And then, but can you explain why the direction of the accelerometer you attach it to the specimen for shear wave measurements is not parallel to the longitudinal axis of the rod wave, the core, but it looks like it is parallel to the radius direction. I may say that is the right way of explaining radius or diameter direction of the core. Why is that?
Oh, sorry, I don't understand where the sentence is too long. Can you
Okay,
explain
all right.
again?
So, yeah, looks like you don't catch my questions. All right, the next question go to 예은비 and also 규정 together because you are dealing with the interpretation and the analysis of the results. And then first of all, I was stunned by looking at the Poisson's ratio you reported over than 0.5. And secondly, I was shocked by the magnitude, the value of shear wave velocities for the granite. Okay, but you were aware of the Poisson's ratio, which is kind of unusual because it's over than 0.5, but you were not aware of the tremendously large values measured. And then the shear wave velocity you measured for rock is almost the same as aluminum. That's totally doesn't make sense to me, right? I'm sorry, not the shear wave velocity. So V sub C, unconstrained compression wave velocity. So if you can, you may share the presentation again, and then let me explain what it is. Sorry, but the time is over 20 minutes already. So stop doing it. But anyway, so those are the things. But I like to hear what you can explain about. So Eunbi and then Kyujong, separately. Eunbi first. Do you understand what I asked you?
No.
No? Okay. How about Kyujong?
Actually, I know the value were not quite successful, but we take our Excel file, which is contain values, but that file means many values.
Okay. Yeah, probably we have to stop because of students are waiting to come. All right. So Jerica, what can you explain? What is your opinion on those values of, tremendously large V sub C?
I believe, Professor, they were not able to do the test correctly. That's why their values are not correct. And also, if you can, I saw on their presentations that, for example, there are two peaks in the on the graph, and they chose the smaller peak rather than the highest peak. So I don't know which is it, but I cannot justify their decision on how they select the V sub C and V sub S in order to arrive for the right Poisson's ratio. But and also I want to say that they wrote on their reason of error in the analysis the reason why they arrived to those things. So
but none of those are persuasive to me at all.
Yes.
So unfortunately, they do not realize what's wrong with them, and then they didn't realize even the higher velocities that it should be. So this, it's like they are just busy, in a hurry to finish up their responsibilities, and then they didn't care about the goodness of the results at all. So that's kind of a disappointing thing a lot. Okay, anyway, so that's about it. And then thank you guys for your coming to the presentation this late. But anyway, I appreciate your efforts. Thank you guys. Bye. And then, so you guys, exit the Zoom session, and we are meeting the other guys. All right. Okay. Thank you guys. Bye.
The students for next group are Kang Na-wi, Kang Dong-hyun, Kang Min-jong, and Kang So-heng.
So everybody is here now?
Kang Na-wi, Kang Dong. Shin Jong-ho is not in the group.
Okay.
But maybe he want to watch or something.
All right, good. Yeah, no problem. Okay. And then the group number?
1. Group number 1.
I got it. All right. Good evening, students. So welcome to this session. So maybe Sewa is waiting for being admitted. She'd like to be in this session for watching over what her friends is doing, how good her friend is doing. Okay. All right. So good evening, students. And then, can I hear something from you guys too?
Good evening, Professor.
Oh, thank you. Yeah, that's what I like to hear about too. Okay. All right. So again, this session is broadcast live right now through the live stream of YouTube. Hopefully somebody, and maybe at the other side of the world and the earth, maybe Indonesia or the States, somebody is watching over us. So hopefully you are not using Korean at all, and then only the official language here allowed is English. Okay. All right. So who is in charge of this presentation? Okay, I'll just nominate it. Kang Nahi, you are the first one in the group. So can you organize this presentation? So I believe you have a privilege of sharing screen too. So go ahead.
Can I start right now?
Yeah, Kang Nahi, what are you doing? You are the captain of this presentation. Okay.
Hello, we are Group 1 and thank you for preparing this presentation, and we'll now start to presentation. Kang Dong-hyun will start the presentation.
Hello, my name is Kang Dong-hyun, the first speaker in Group 1. Before we go any further, I would like to appreciate to the Professor Cho, who taught us in lung mechanics lecture, and assistant Jerika and Hazik, who prepared and guided the whole experiment. Then let's begin the presentation with the contents. Our presentation is in 6 steps: purpose, basic theory, experiment equipment, procedure, result, and finally analytic and conclusion. I'm going to talk about the purpose and basic theory. The first topic is purpose of the test. Resonance test is ultimately intended to detect cracks or lock cleavage at non-destructive state. In our test, we can estimate the dynamic properties of lock specimen, such as modulus of elasticity, Poisson's ratio, by getting specific resonance frequency and wave velocity. Our resonance test is divided into 2 types, load wave and shear wave. Each wave is generated by impacting at the specimen and detected by attached sensor. Through the information from the sensor, we can obtain the lock properties and further analyze the entire state of lock. In our experiment, the Young's modulus and Poisson's ratio were mainly obtained as a result. Then how can we get the result? Just by impacting on the lock specimen. In load wave case, when we impact on the bottom side of the specimen, the stress wave occurs and repeat the reflection as a picture shows. After that, the sensor, accelerometer, detect the wave frequency, and we can get the wave velocity and modulus from the below formula. The shear wave is same method. Impact on the specimen makes the torsional shear wave and repeat the reflection and apply to the below formula to obtain such values. And now I'd like to hand over to next speaker.
Hello, my name is Kang Nahi. Now I will explain the test equipment of experiment and procedure. There are 4 types of equipment. First, dynamic signal and analyzer, accelerometer, rock samples and aluminiums, and instrument hammer which hits the specimen. Also, I will explain how to proceed with the test. First, before starting the test, measure the length and diameter of the specimens. Next, enter the weight, length, and diameter of the specimen. And then enter the data equation DAQ configuration, turn on velocity and test the root wave and S wave to 35,000 values. When the experiment is ready, start ROD wave test. Connect the cable to the accelerometer on the flat top and use a hammer to hit the flat top of the specimen. After stopping the test, select the peak point of the graph and select the road wave. The third step is shear wave test with OSR. First, hit the center surface of the sample to find the bending value. And remember the bending value. And then, to find the shear wave value more easily, we hit the lower part with the same distance as the position and select the peak point of the shear wave. Finally, we get the result of test. Thank you.
Hello, my name is Kang So-heng, and I'll talk about the results of our experiment. The first specimen ID is sample 1, and on the left side there is data of specimen, and in the middle there are road wave peak and shear wave peak. From these values, we can get measurements of the test, like the table on the right side. Its Poisson ratio is 0.34, and to check this value, I calculated by hand. The left side is measurement of the test, and right side is my calculation. I calculated the Young's modulus and shear modulus, Poisson's ratio, and p-wave velocity. As you can see in the red box, my calculation of Poisson ratio is same as measurement as 0.34, and the other values are also same. The second specimen ID is sample 2. Is also the left side is specimen data and right side is measurement of the test. Its Poisson ratio was 0.29. And also measurement of the test and my calculation of Poisson ratio was same as 0.29. The third specimen ID was sample 3, and its Poisson ratio was negative. As you can see, values are same as what I calculated myself. The last specimen Poisson ratio was 0.15. Also, the measurement of the test and my calculation is the same. This is summary of our experiment results. And then let's talk about the analysis and conclusion. The first specimen was aluminum, and its actual Poisson's ratio is 0.334, and our experimental Poisson ratio was 0.34. There is little bit difference in value, but it is negligible, so we think the test was proper. And the second specimen was granite, and granite's actual Poisson ratio is 0.2 to 0.3, and our experiment value was 0.29. So the value is in the range, so we think the test was proper. But the third specimen was granite too, but our experimental value is negative as minus 0.02. It is invalid value, so we will talk about this in later. The last specimen's experimental Poisson ratio was 0.15, so we can think it is concrete because concrete Poisson ratio was 0.1 to 0.2, so our experiment value is included in that range, so we can think the last specimen as concrete. Thank you.
Is that it?
This is Han Min-jung, and I explain our discussion. The larger Poisson ratio, the easier it is to expand. Therefore, aluminum ware with the Poisson ratio is the most likely to expand. And second, the solid wave velocity can be used in that indicating the degree of fissure development of samples. So measuring the sound wave speed, we can know the degree of fissure of the sample. And we found that even the same rock could have different Poisson ratio, and we discussed why these fissures were obtained. If the fissures are arranged parallel to the loading direction, the cracks are open and Poisson ratio are higher. Therefore, even if the two rocks are fissure of similar density, the Poisson ratio is different depending on how many fissures are parallel to the road direction. Fissure may have occurred during the coloring process, which are not visible with the naked eye. And hammer is controlled by hand. It is hit with an inaccurate strength. Most natural metals in nature have positive value. We know that the Poisson ratio should be positive, but we got the negative value in one rock. So we've been discussing why the Poisson ratio is negative. Torsion makes fracture waves and shore waves. These two waves are mixed and errors occur in the resonance frequency. Therefore, measurements using two accelerators should have impact the nodal point because bending waves occur at the nodal point. We measure it with one accelerator. We put an accelerator at the nodal point and hit the hammer and opposite nodal point. The hammer is controlled by hand. It was not possible to impact the exact location, and therefore the shore wave may not have completely eliminated the deflection wave. Thank you for your attention, Professor.
Okay, thank you for your presentation. Looks like you spent quite a time for preparing the material today, and then surprisingly, I agree with some of the students, speakers' opinion and discussion, but some other students, some other speakers, unfortunately, I do not agree totally with them at all. For say, let me ask you guys, 나희, 동현, 소행. I'll ask you, three of you. Do you agree with Min-jung's discussion? Have you guys talked to each other about the final discussion and conclusions? Soheng, can you express any opinions?
We discussed, but not fully discuss about it. So
yes. That means Min-jung's opinion is not yours.
We discussed about it, but not all of them is her opinion. Yes.
You know why? Looks like Minjung is coming from, let's say, Mars or Mercury or something like that. She did not, I'm pretty sure, she did not pay attention to my lecture at all. I have never used the word sound velocity in the class, and she is using sound velocity. I'm totally upset about the choice of her word. That means she is not referring to my lecture or our guidance of the test, resonance test at all. And maybe she was referring to something else, or she got some advice from somebody else's. I'm so much curious about it. So Minjung, you know what? I'm totally disappointed with your conclusions and then discussions. I do not agree any of yours. Honestly, I do not agree with any of your discussion. I'm so much upset. I have never been this upset before in, let's say, last 10 years. This is the worst presentation that I have ever heard. So this is not just your problem, and this is coming from all of your members. So they did not contribute to your discussion at all. I don't understand what happened to this group. Looks like Soheng has a good idea what's going on, but she did not answer. She did not express her opinion about Minjung's the discussion anyway. So I'm sorry about that. I was so sad about this presentation. I like to close this session, and then I have lots of questions, but I like to close this session. I need to calm down a little bit. Okay, sorry. That's it for you guys. Okay. All right. So please exit this session, and then we need to continue with the next group. Okay, please. All right, so the next group, Jerica.
The next group is group 6. Shin Jun-sik, Shin Jong-ho, Shin Ji-hoon, Yang Se-hwa. All of them are there.
All right, so group number
6.
Got it. Thank you.
교수님, 신지훈 학우님이 지금 못 들어오고 계시답니다.
오케이.
30분 전부터 계속 기다리고 있었는데.
맞아. 미안해. 내가 조금 전 그룹에 대해서 너무 열받아가지고 세상에 이런 일이 없었는데 도대체 조금 전 그룹은 도대체 뭔 일을 한 건지 그룹 1번 멤버들 사이 소통도 전혀 없었고 혼자서 스토리를 만들어냈어요. 네, 이런 일은 없어야 되는데 한 10년 과거 10년 동안에 이런 일은 진짜 없었어. 진짜 최악이야. 내가 이렇게 나쁜 표현을 쓰질 않는데 진짜 너무했어. 그룹 1번은. Okay. Alright, group 6. Group 6. Yes, okay. If you guys ready? And then let's go. 지훈이가 제일 먼저 이름이 올라와 있는 걸 보니까 지훈이가 전체 책임을 오거나이즈를 좀 하시지? 지훈아, 근데 화면이 이상하다. 얼굴이 막 번쩍번쩍번쩍해. 백그라운드를 카메라 문제인가? 혹시 백그라운드 설정을 뭐 이상한 걸로 해놓은 거 아닌가? 줌에서?
아닙니다. Is that okay?
Yeah, that's now.
Thank you.
What happened? Did you have a psyche light on in your room?
I think it made me sit in dark.
Okay. All right.
Can I
let's go.
start our presentation?
Sure, go ahead.
Thank you. Hello, this is Team 6 of the presentation related to the Lacquer test. Our team members are Taehwa Yang and Junshik Shin, Junho Shin, and Jihoon Shin. Before proceeding with the presentation, I would like to thank Professor Hazik and Jerika for helping us study the theory of the Lacquer test. Now, we will proceed with our presentation. The table of contents is as follows. The purpose of the Lacquer test is to obtain Young's modulus, Scherr modulus, and finally, Poisson ratio. I will explain the three theories necessary for this experiment. First, the load wave generates a stress wave by attaching an accelerometer to one side of the specimen and then applying impact to the other side. The wavelength is 2L and the velocity is measured using the resonance frequency obtained from the experimental lizard and get Young's modulus. Next, let's talk about the Scherr wave. Before that, OSR technique is required to carry out of this experiment and measure it. If you look at the picture, there are nodal points on the both sides. At this time, since the bending displacement is minimal, the torsional wave is measured. A Scherr modulus requires that the accelerometer and hammer impact point be the same distance from both sides. For the Scherr wave in this experiment, the Scherr wave velocity and Scherr modulus obtained through the resonance frequency and 2L can be obtained. The final Poisson ratio is obtained by substituting the result obtained through the above two experiments into each equation. This is Jihoon Shin, who presents the purpose of theory of this experiment above. Next, Shin Junshik will proceed a presentation.
Okay, thank you. Next part is the equipment required for the free resonance test. Two rock and aluminum specimens where the density and other parameters are already known were used for the experiment. You might wonder why aluminum was used in this rock experiment. Since aluminum has no pores and fissures, unlike rock, we can compare and get some integrity about the results. Accelerometer deployed on the base part of the cylinder specimen was used for the rod wave measurement, and the one on the curved surface was used for the shear wave measurement. The location of the accelerometer has been determined based on the OSR theory as mentioned on the theory section. Last equipment is called Polka, which is basically a computer that can log the acceleration data from the vibrating specimen. It has optimized software for the free resonance test, so as soon as you hit the specimen with hammer, the measured acceleration and frequency directly appear on the screen. Also, it automatically calculates velocity, elastic modulus, and Poisson's ratio, which is wonderful. And move on to the next part is the procedure part. First thing you need to do is to set up the software on the Polka. Turn on the software and adjust some parameters and settings based on the purpose of the experiment and types of the specimen. After all the settings are done, proceed to the impact stage. You have to make sure that you are hitting the right place. It is very important as it changes the results of the experiment significantly. For the rod wave, you need to hit the base center of the specimen with slight power. For the shear wave, the hitting spot should be L-2D from the accelerometer and the same line with the sensor. If you miss this point, the result of the experiment would be unmeaningful because it does not fulfill the basic assumption of the OSR theory. After heating, the data would be appear on the Polka. Examine the values and repeat the test until you get the satisfactory data. Mostly ideal results of the frequency graph should have only one dominant peak.
Hello, my name is Sewa Yang. Then now let's see the specimens. The research of specimens. The first specimen is granite, which is 15 centimeters long. The data is like that. We can measure the peak road wave frequency of the first rock and the peak shear wave frequency. We choose a consistent value through approximately and 3 iterative measurements. From that, we can obtain the road wave velocity and elastic modulus by using Young's modulus, and we can obtain the shear wave velocity and shear modulus. The second specimen is granite, which is 10 centimeters long. As the same way, we can measure the road wave and shear wave in the same way. As the same procedure we mentioned before, we can get the research of the granite. The third specimen is aluminum, which is 10 centimeters long. We also obtain the road wave velocity, elastic modulus, the shear wave velocity, and shear modulus in the same way. From the elastic and shear modulus, we can obtain the Poisson's ratio. And from the Poisson's ratio and shear wave velocity, we can finally get the P wave velocity too.
This is our result table. Our rock 1's measured Poisson ratio is 0.2163 and granite's Poisson ratio is 0.2 to 0.3. So you can tell that this was a reliable test. Also, our rock 3's measured Poisson ratio is 0.3406 and aluminum's Poisson ratio is 0.35. So rock 3's test result is reliable. But we have problem with rock 2. We measured rock 2's Poisson ratio as 0.3417, although the actual value of Poisson ratio is 0.2 to 0.3. In fact, we had another problem while testing the specimen 3 and specimen 1 because the Poisson ratio was measured under 0. So we discussed about these problems and found out some reasons why we had negative Poisson ratio and our rock 2's unreliable test. The first reason is control error from human. And the second reason is micro vibration on the test. And finally, the most important reason is cracks and anisotropy. As all know, Poisson ratio is defined like this. But if the specimen has the cracks, it needs more time to cross the cracks. So if VC became smaller than root 2 VS, Poisson ratio can be negative. Special thanks to Professor Zhou for giving an opportunity to experience another knowledge. And feedback, please.
Okay, let me go over your presentation quickly. It's already 7:55. We are supposed to finish in when? Jerica? 8 o'clock p.m.?
No, 8 o'clock for their session. 8 o'clock.
Yeah.
They're the
Okay.
third group.
All right. First of all, thank you very much for Chung-ho's discussion. Nobody has expressed the possibility of cracks, influence on the wave velocities, and he is the only one so far. So I think he got the right point. I appreciate it very much. I'm so happy to hear that. In case of Ji-hoon, let's go back to Ji-hoon's presentation. And you did pretty good job, but I just would like to make sure you know the difference between V sub C and V sub P.
Can I watch the P?
Oh yeah, so the question is, what is the difference between V sub C and V sub P, especially in terms of measurements aspect?
화면 공유 좀 부탁드릴게요. PPT가 있고. A professor asked me about 3C, different about 3C and 3P, right?
V sub P wave measurements. Okay.
I just sorry, I can't answer about that question.
Oh yeah, I didn't expect you answer correctly, but I wish you to have some brief idea what is V sub C at least. And right here we are using the name rod wave, right? So some student may pronounce it like a ROD wave. I mean, probably they understood it's kind of abbreviation of the full names, but it's not. It's just a rod and like a stick, but the rod is like a one-dimensional. And so it is the compression wave with no constraints at all. So we call it unconstrained, the compression wave. But on the other hand, P wave is constrained wave. So P wave is much faster. So what we measure right here, and the boundaries is not constrained. So we are measuring unconstrained compressive waves. So you see the down here unconstrained compressive waves. So hopefully you got the point, but unfortunately not. It's okay. All right. In case of Sehwa, you just reported the values of Poisson's ratio and then the velocities of the granites, and then you didn't explain about it. And then, but hopefully, I wish you have a. I mean, the Poisson's ratio is over 0.333, and then maybe you are wondering. You have to be wondering, is this value valid? Because the rock has the ratio. I mean, the Poisson's ratio from up to 0.2 or 0.3 or something like that. It doesn't go over that much, but it is. I mean, two of them is already 0.34. And so when, in this case, you'd better go back to your measurement, hopefully. Can you go back to the shear wave measurements and then the power spectrum of shear wave measurements? Can you go back to previous pages? I saw one of them. No, not this one. Could you go back to trace? The power spectrum. Not this one. Oh yeah, right here. Okay, next one. The one just before this page. Yes. So yeah, so that was rod wave actually. I thought that is a shear wave, but it's not. It's a rod wave. But looks like your measurement is kind of not so much clear even in the rod wave, but surprisingly shear wave is okay. So in this case, there are several peaks you see. So you may be wondering which peak is the right one to choose. Okay, so you have to wonder about it. And then, so maybe there's some thing that some more efforts should be put in these measurements. But unfortunately, yeah. Anyway, so the questions for Sewa, but I was complaining about you were a little bit I mean, the insufficient efforts on the measurements. Anyway, again, Jung-ho, you did a good job for your discussion on the negative Poisson's ratio. Okay, all right, good enough. We don't have enough time, so we have to move on to the next group presentation. All right, thank you guys, and then good evening. I'll see you in class. Bye.
Thank you, Professor.
Sir.
Okay, bye.
Group 5, right? Yes.
So how many more groups do we have right now?
Only 2, Professor. Right
Oh,
now
okay.
is group 5 and next
Group
is
2.
the last group 2.
Professor.
Mm-hmm.
Kang Minjong messaged me about the sound velocity.
Okay.
Maybe we can discuss after, or should we discuss? We can discuss after, I think.
Yeah. So what is her message again? What
She's
is the message
asking,
on? Mm-hmm.
in your presentation, you have measurement of velocity of sound waves in core specimen. You have a presentation. She sent me a slide, and then she said she wants to know more about it because of what you said in the presentation.
All right. So I couldn't control my mind.
Yeah, I know, Professor.
Yeah. Okay. Anyway, so there are several points that, so that drove me crazy about. Okay. All right. So
so the next presenter is Group 5, and then
Group 5. Okay.
The members are Park Song Min, Park Chan Yong, Song Ji Mi, Song Min Yok.
All right, let's go. You have
They're
50
all
minutes
here.
for presenting.
Yes. May I share my monitor now?
I beg your pardon?
May I share my monitor now?
Oh, I think it is.
Okay, thank you. Can you see the presentation?
Go ahead.
Thank you.
Shall we start?
Go ahead, please.
Okay.
Yep.
Good afternoon, Professor Zhou. We are junior.
Park Song-min.
Park Chan-young.
Song Ji-mi and
Song Min-hyuk from Team 5.
Today, we are going to perform presentation about the lab test that we have done. I'm first speaker Song Ji-mi, who will talk about the contents and theory. Our presentation will follow the steps in the slide. First of all, I will say a few words about the theory. Then, our next presenter will speak about the lab test that we have conducted. At last, we will go through the discussion and results. First is theory. When talking about the resonance test, Poisson ratio cannot be left out. The definition of Poisson ratio is transverse strain divided by axial strain. We call it nu, and it doesn't have any unit since it is an expression of ratio. Poisson ratio equation can be expressed as E divided by 2 times G minus 1. We can get E from the rod wave test and G from the shear wave test. Following what I said earlier, we got the resonant frequency Fc from the rod wave test and got resonant frequency Fs from the shear wave test. Later, our next announcer will handle this part in detail. The reason that Poisson ratio is important is that it is characteristic index,
which means Poisson ratio has a specific value depending on the material. As you can see on the chart on the slide, for example, aluminum has 0.33 value and gold has 0.42 value. While studying the Poisson ratio, our team was curious if it is possible to have negative value of Poisson ratio. We confirmed several papers about the negative Poisson ratio and got the answer. Anisotropy can make the Poisson value negative. Also, oxidic materials which exhibit unusual and counterintuitive mechanical behavior also can have negative Poisson value. Representative examples of oxidic materials include oxidic polyurethane foam and alpha crystal plates.
Hi, my name is Hongmin Park. Before starting the presentation, I would like to thank the professor for giving me this opportunity. Then I will start the presentation. My part is introduce equipment used in the Rockwell test. There are 5 main equipment in the Rockwell test. First, specimen. Basic characteristics of specimens such as length, weight, and diameter are measured, and test results are obtained through this. So before starting tests, we make sure that specimen condition is well. Second, an accelerometer that measure the resonant frequency of a specimen generated in the Rockwell test. Third, a cable that connects accelerometer and specimen. We have to check if there is anything wrong with the cable, such as, for example, this connection. First, an impact hammer that applies an impact to the specimen to generate a resonant frequency. Finally, software that analyzes the result obtained from the Rockwell test and drives various values, for example, Poisson ratio and resonance frequency. Thank you for listening. The detailed test process will be explained in the next part.
Hi, my name is Chanyoung Park. I will introduce Rockwell test process. Next page. First, measure specimen weight and volume. Connect accelerometer attached to the specimen to analyze signal to dynamic signal analyzer by use cable. And second, before the test, set the basic value by using input channel program. Next page. If we measure by using a hammer, impact parallel to the core axis of the specimen, and then we can get load wave frequency. Next. If we measure shear wave by using a hammer, impact perpendicular to the core axis of a specimen, and then we can get shear wave frequency. So we can calculate load wave and shear wave velocity by using measured frequency. Like the result, we can calculate Young's module and shear module and Poisson ratio by using formula. And next presentation, continue next presenter.
Hi, my name is Song Min-hyo, and let's see the results of this experiment. It's beautiful, isn't it? We can check the experimental results at a glance with a file of .xls extension. Data analysis becomes a piece of cake. Anyway, what should be noted here is Poisson's ratio. As mentioned earlier, the system is verified through aluminum that has proven Poisson's ratio. In addition, we can see the Poisson's ratio of rocks that do not know their physical properties. Please look at the picture and the results. According to the assistant's prior guidance, the normal Poisson's ratio of the rock specimen is close to 0.3, and the aluminum specimen is also close to 0.3, as introduced in the theory. But the results are quite different, as you can see. How much and why it different from the predicted value? Specimen 2 was less than the expected value of 0.3. This is the result of the rod wave's travel length being longer than the shear wave due to the anisotropy mentioned in the first chapter. In the case of specimen 3, a negative number came out in the first experiment, and the result was when a different peak was selected. You can see the value 0.71. This also appears to be the results of the planar anisotropy of aluminum. Thank you for listening, Professor Joe and Sarika Hazik.
Okay, just a moment. Okay, first of all, my question goes to Song Min-hyuk, and then I was not so much clear to catch what he was explaining about the high Poisson's ratio for aluminum. Okay, and then can you go back to the previous pages explaining if is this the one or the one before this?
Yes.
This page. Okay, would you briefly repeat the reason of higher Poisson's ratio than the regular, the normal, what is expected? We are expecting 0.333, right?
Yep. The first approach, we can get the negative value, but in the second test, we think Poisson's ratio can come out negative value, so we picked another shear wave frequency, but it was not correct frequency peak because we have two peaks, but we take the lower peak, so it was actually error from experiment, and I think the negative value was right.
Some other groups, only one group, searches through the internet, and then they found the two different types of aluminiums, and for each aluminium, and then they reported the expected Poisson's ratio and then other properties, and so what they found is the aluminum 6061, and it should have a Poisson's ratio of 0.333 something. Yeah, so actually it is right. I purchased aluminum 6061. I know the right type, right model of the aluminum. So the value should be 0.333. And then unfortunately, your measurement shows two different ones. The first one is a negative, the second one is 0.71. So neither of these is right. And so probably if you are aware, if you guys are aware, the aluminum does not have any impact. I mean, any anomalies. The outer surfaces or whatever, and then you should expect pretty close the Poisson's ratio to 0.333, but it's kind of a little bit disappointing. You didn't try to have another measurement to give you more reasonable values of Poisson's ratio. Probably also you compared the shear wave velocities, and also so that's one thing that I was not happy about your measurement. Okay, and then if I, as on the other hand, I mean, if I use a little bit different expressions, you should try different way of generating impacts, or maybe different types of impact sources, and then to generate the right, reasonable shear wave resonances or rod wave resonances. And then if I were you, or if I were you in your place, I would do maybe try a lot different things to reach the right ones. Okay, but anyway, that's one of my opinion. And then if I go to Chanyoung, and then the picture you showed for shear wave measurements, that is not the right one. So in this lab test, I told you to utilize OSR technique, optimal shear wave resonance technique, and then that one that you showed through the picture, by the picture, and that's old traditional method. And then the problem of that technique has a added mass at one end, so that is changing the system because it is adding the mass to the end. So the theory should be changed, because the theory does not include the additional mass at the end. So that is changing the resonant frequencies and then all the others. And so these days we are not using that added mass at all. And then so we have to we have to use the procedure suggested by the OSR technique. So that's one thing. Probably I think it's just a simple mistake. And then if I go to Seungmin's presentation, and then it looks like you have a little bit strange diagram or symbol or drawing for the accelerometers attached to the sample, to the rock core, for shear wave measurements. Would you go back to the previous pages? There was, if my memory serves right, and then is this the first page of explaining the test equipment? Is this the first page? Okay. And then next, maybe then I was confused with somebody else's. Okay. All right. But anyway, so can I ask you, Seungmin, regarding this is kind of critical, so I'd like to hear about why do we attach the accelerometer for shear wave measurements tangential direction to the circular, the cylindrical specimen? Can you explain?
Sorry, I don't know.
You have no idea. Okay. Maybe it is easier to put the accelerometer vertically, right at the surface, right? The bottom goes to the surface. But we are like slanting to the lateral direction, in other words, tangential direction. You have no idea. Okay, that means you don't understand the shear OSR technique at all. Chanyoung, can you?
Yes.
Can you explain why the shear wave, the sensors, accelerometer for the shear wave measurements attach the tangential direction to the cylindrical specimen?
Because I think it's different to
Okay. How about Minhyuk?
Thought this technology using the resonance of the rock, so we have to make parallel the hammer maiden wave and the accelerometer direction, so it attached vertical tangential for specimen.
Yeah, that could be right, a part of the reasons, but actually there is more important fact that we have to orient the accelerometer to the tangential directions. In other words, why do we have to hit the impact hammer to the tangential direction rather than the perpendicular direction to the surface of the cylinder? Jimmy, I think you did a wonderful job for explaining the negative values of Poisson's ratio. So that's a real physical things, and then I'd like to go back to the question again later on. But can you answer the questions that I brought up right now?
In my opinion, I thought that it's really important to catch the wave. So when we were conducting the experiment, we had another question, like if it is all right to conduct this experiment on the table, like maybe professor's questions is related with my question, and the vertical attachment will dismiss the impact of other noises, I think.
Okay. All right. So probably that goes with Minhyuk's explanation too. But basically, or more fundamentally, we like to be focused on the shear wave itself. We are not talking about pure shear wave. We are talking about torsional shear wave here, right? But Jimmy, can you tell the difference between pure shear wave and a torsional shear wave by chance?
Sorry, Professor, I have no idea about that.
Okay, yeah, probably I'm asking too much. I'm expecting too much, you guys. All right, so okay. Anyway, go back to Jimmy's wonderful findings, and then she found through the literature review very nice reasons for negative Poisson's ratio. There are two different things, but I'd like to hear about the first one, anisotropy. Can you give us more detailed explanations on the anisotropy, specifically in the aspect of, let's say, Poisson's ratio?
Like the density is quite important factor of the Poisson's ratio, and that's why anisotropy influence the Poisson's ratio. Like the different strengths interactions in the specimen result the negative Poisson's ratio.
Okay. By the way, what is the definition of the word anisotropy, first of all?
Can I say in Korean?
Not really.
Like
you can make bring up some examples for explaining. I think
like
that's better.
Uneven and uncorrected. I want to define it uneven and uncorrected.
No, that's not right. So that's why you are not explaining correctly. Yeah. So un is like a prefix. Isotropic is another. Yeah, maybe it has a Greek root, and so that means in terms of directions, let's say x direction, y direction. So depending on the directions, the material property is going to be changed. Okay, so that's anisotropy. For say Young's modulus in x direction is not the same as Young's modulus in the y direction. So right here, let's say I don't have to lecture on this right now. But anyway, so and the whatever the unconstrained compression wave velocity, wave propagation is not. Going on or is not transferred or propagated. The waves are not propagated. Due to some anomalies included in the specimen. For say the unconstrained compression wave velocity, waves are propagating parallel to the longitudinal axis of the cylinder, and then there is some micro cracks inside, and even though we do not see outside, and that micro cracks which was included in the magma buildup, and then so that is like a blocking the propagation of the unconstrained compression waves. So that is slowing down the compression waves, in other words. But on the other hand, the shear waves does not have any impact or influence from the anisotropy. So shear waves is measured as usual, but P wave or the rod wave is measured smaller. So that is causing negative Poisson's ratio. That is why they are using the word of anisotropy in this case. Okay. All right. Okay, that's good enough. And then I like Jimmy's efforts or contribution to this group's presentation pretty much. Thank you so much. And then now you can leave the Zoom, and we are expecting the last group to come in today. Right. Thank you guys again. Bye.
Yep.
Thank you, Professor.
Thank you, Professor.
Sir.
Professor, may I ask you something for last?
Yeah, what is it?
You taught the small fracture in rock core, and that makes the anisotropy. But if the wave can pass the fracture?
No, I didn't say fracture. It's like a small void inside. It's like the void is organized. Let's say the perpendicular to the longitudinal directions. So those are aligned to that direction. So when the constrained compressive waves are trying to travel through it, and that because there is some gaps between the material or the structures, and then those are delaying or slowing down the propagation. So that is causing the slowdown of the velocities, and then that is leading to the negative Poisson's ratio.
Yes, thank you. I understand. Thank you, Professor.
All right.
Yep.
Okay, so today we have the last group, and then group number is Jerica?
2, Professor.
Group number 2.
2, okay. All right, good. So
the members are all here.
Okay.
Kwon Namjoon, Kim Kwon-hee, Kim Ki-yeol, Kim Dong-chan.
All right, so 4 of them, okay?
Yes, Professor.
All right, so if you are ready, please go ahead. We are ready whenever you are ready too.
Yeah, I think we're ready, Professor. So
Go ahead,
we're going to start right
please.
now. Hello, we are group number 2, and we're going to present about the resonance test of different kinds of materials. And my name is Dongchan Kim, and I'm going to talk about the theory of the experiments. Next slide, please. And here is table of contents. The first one is theory, and the second one equipment. And the third one is procedure, and the first one is result, and the fifth one is analysis, and the last part is conclusion. The next slide, please. First, the theory. In various fields, there are numerous ways to determine the characteristics of materials, and the resonance test is considered as one of the most effective methods to estimate the status of the hard materials like concrete and rocks. The resonance frequency is defined as a natural frequency where a medium vibrates at the highest amplitude. So by measuring the frequency of the material, we can calculate the velocity of different types of waves, and this enables us to grasp the characteristics of the specimens. In these experiments, rod wave, which is also known as unconstrained wave, and the shear waves are used to determine the results. Next slide, please. Rod wave is a type of compressional wave which appears the similar characteristics of primary wave, and its particles motion is parallel to the wave direction. Rod wave has a long wavelength, and this enables the particle to vibrate until the outer surface of the specimen, so it provides the unconstrained state. To measure the rod wave, a frequency sensor should be attached at the one end of the specimen, and the hammer must impact at the other side of it. From the estimated frequency, we can solve the velocity of the unconstrained wave and elastic modulus of the specimen by using the equation on the slide. Next slide, please. And for the shear wave, it is the type of transverse wave that occurs in an elastic medium, and the particle's motion is perpendicular to the wave direction. Usually, we use the torsion force to get the data, but in this case, the bending wave can be occurred, which might cause the error in the shear wave measurement. Therefore, we use OSR method to avoid the effectiveness of the bending wave. Unlike the rod wave measurement, the sensor should be placed at the side of the specimen, and the location of the hammer impact should be exact the same distance from the other side. So by using the resonance frequency of the shear wave, we can also easily get the shear wave velocity and the shear modulus. Next slide, please. So after solving shear and elastic modulus, Poisson's ratio and P wave velocity can be determined as well by using the equation on the slide. Next slide, please.
Hello, my name is Kyo Kim, and I'm going to present about equipment and specimen for test. We need to prepare the following: scale, hammer, cable, experiment stand, and dynamic signal analyzer for gathering all test data. Next. And two different specimens like these. Specimen A has a diameter of 50 millimeter, a length of 100 millimeter, and a weight of 514.53 grams. Specimen B has a diameter of 50 millimeter, a length of 200 millimeter, and a weight of 1,177 grams. And both specimens are the same material, granite. Next slide. The test is carried out as the form of hitting the specimen with a hammer and checking the graph that results from the data. Before progressing the test, we need to set up something. First, set IE PE on in DAQ and range of ROD and shear wave to 35,000 volts for accurate test. After that, measure and input the weight, length, and diameter of the specimen to be tested. Next slide, please. If done settable, impact a hit point of specimen with a hammer. After, arrange the cables so they don't be tangled. When measuring ROD, Connect the cable at the center of upper surface, and the center of the lower surface becomes the heat point. At this time, the connected cable and heat point were parallel in nature. In the case of shear, connect the cable to the side about 21 millimeters from the top of the specimen. The heat point will be the part at a distance of 21 millimeters from the bottom. Two distance connected cable and heat point are the same. Next slide. If tests are progressed like above, we obtain the graph the following. The resulting values of specimen A are shown as you check this slide. Detailed values will be mentioned in the analysis part. And next slide, please. And the specimen B is shown as this. Here, left side, the Poisson's ratio becomes negative. So we thought that the Poisson's ratio was wrong at the time. So we ran the experiment again. Its values are shown on the right side. Next slide, please. This is a table that summarizes the results mentioned above. Thank you.
Okay, thank you, dear Kim. Hi, my name is Goni Kim, and now start the analysis part. We compared and analyzed the experimental data with the results obtained by inserting it into the formula we have run before. First, in the case of specimen A, the resonant frequency of ROD was 2039.1, and the resonant frequency of shear was 12,392.6. The elastic wave speed was calculated through the formula EFR multiply L, converting this into velocity, and Young's modulus and shear's modulus were calculated. Of course, the density, which is the physical property of the specimen, was also obtained by measuring the actor specification, when we have already mentioned before part. And finally, Young's modulus was 42.09 gigapascal, and shear modulus was 16.09 gigapascal, and Poisson's ratio was 0.307. Also, in the case of P wave, it was faster than shear wave. And for specimen E, the resonance frequency of the ROD was 9,228.52, and the resonance frequency of the shear was 6,035.16. Like specimen A, when calculated by applying the formula, Young's modulus was 40.84 gigapascal, and shear modulus was 17.47 gigapascal. And the Poisson ratio was 0.169. In addition, the P wave was 3,825.43, which was faster than the shear wave.
Hello, my name is Kwon Namjoon. Let me announce the conclusion. Through this resonance test, now our group is able to understand the formulas related to the process of obtaining rod wave and shear wave. As you can see on the screen, the velocity can be obtained by resonant frequency and the length of the specimen. And with the density, elastic modulus can be obtained by rod wave, and shear modulus can be obtained by shear wave. In addition, through these two waves, the Poisson's ratio can be obtained. Next, please. In the test of the specimen B, there was once a negative result in the Poisson's ratio. Next, please. This is summarized through the following equations, and it can be seen that a negative value comes out when VC is less than √2 times VS. Next, please. And sometimes there are several frequencies instead of one. The reason is that when we did the test, the specimen was hit several times, or the direction and position of hitting was wrong. Next, please. This is the end of our presentation. Thank you for listening.
Okay, thank you very much for your wonderful presentations, and then mostly the presentation was pretty done well, but I have a couple of questions for your the results specifically. Let's say, can I take a look at the last page? Explained by Kwon Namjun.
Yes, Professor.
Okay, is this the last one, or let's go back to previous one then? Okay, right here. All right, next one. No, the same page, but with a little bit, additional comments on the figure. So multiple picks.
Maybe several frequency.
Oh yeah, that's right. Yeah, that's the point. Okay, yeah, that's the thing that I like to ask you about. So you looks like you experienced the several frequencies. Maybe we have to use several peaks rather than frequencies. Okay, several peaks obtained or measured through the measurement. So in this case, you are saying to me, Jerica and Hazik, please. Express your opinion on what I said. What do you think? All right, so looks like you're saying you did correctly, but systematically that happened in some kind of, this kind of situation, right? And that situation is hit several times. That means multiple hits. So we are supposed to make just one nice hit, but you made a several da-da-da, right? That's what you said.
Oh,
okay,
Professor, I think what they are saying, they tried several times.
Several times, but several times of try does not give multiple, several frequencies like this. Only this is coming from only one measurement, right? One hit.
Yeah, because it says average is one. Yeah, you're right.
Okay. And then the direction and position of hitting was wrong. So when you have a, let's say, slanted angle, or you, let's say, you hit a, let's say, a little bit offset from the center position or something like that. Is that what you're saying, right, Namjoon?
Yes, Professor.
Yeah, but you know what? I have totally different opinions. And if you are saying maybe that's part of the reasons to cause this kind of multiple peaks, and then we can say, okay, this is not done correctly, so we totally neglect it, and we are repeating the test again with the good hits and good spot. And so you have to report the good one only, right?
Yes, we did it.
Okay. And but why do you show this one? If I were you, I would not show this one at all. I just would like to show the good ones only, right?
Sorry, Professor.
And but I mean, based on this, I may say this is the best result that you could get.
Professor,
right?
Can I talk small one thing?
Okay, go ahead, please.
When we have some experiment in the past days, we have clean data. Which one is data Poisson ratio is negative, not like this figure.
Okay.
But because we use this image, as you can see, the test is so being in the so very fast. No, you know what I'm saying? So when the Poisson ratio get minus value, and we just remove this figure and go ahead of experiment. But Mr. Hazik tell us you should go some project. No, you should explain about this negative value. So we choose this figure as hurry. So yeah, that's all I wanted to talk to you.
Okay.
What they meant, Professor, they are late for the test, and then the other group are coming, and then they cannot like proceed this test like for a longer time because there are other group are waiting.
I
So and then they are they trying like a lot and they satisfied with this result. And I just say if you're satisfied with it, you need to explain why you get negative value. Yeah.
Okay, so that means you were not given enough time to make a good measurements. So this is the only opportunity or the only measurements that you could save in any case, right? Okay. All right.
Thank you,
Let me
Professor.
explain a little bit. Okay.
Professor, I want to add something.
Yeah, go ahead.
If you can see on their rod wave as well,
all right,
the value they selected is not the peak.
Yeah, you're right too. But actually, the frequency itself is pretty small.
Yes. I understand. But what I'm saying, Professor, is I just realized in most of the groups that presented tonight,
that's right. Yeah,
they are not selecting the peak, the frequency. They are I know the difference is minimal, but what you want is.
I think Jerica already explained to them, like doing one procedure, full procedure, and then let them do by themselves.
Okay, but anyway, just with given in a limited time given, and they were not instructed to perform the test correctly. So probably this is the best that they can do. But unfortunately, and then probably they are like trying to avoid the negative Poisson's ratio, and so that might drive them to a wrong direction of getting the results. So that's kind of sad. Okay, 기열. And then probably your pronunciation of the Poisson's ratio, looks like a ratio. It's a little bit awkward, but hopefully you can pronounce it later correctly. But anyway, again, I'm saying the negative Poisson's ratio is a still good one. And what do you think?
Sometimes negative values are the good point for I think our specimen have fishes or something in the rock, so these negative values are not sorry.
Okay, yeah, maybe you were too much nervous about my question, so probably you would say more about that. More than just what you explained, I believe. Okay, anyway, let's go to Dongchan. You explained the theory about, beyond this testing technique, And then I'd like to ask you about, I mean, you were pretty good in explaining the wave propagations, showing the whatever the kind of diagrams of propagation. And then can you explain the difference between pure shear wave and torsional shear wave?
I think the difference between the pure shear wave and the torsional shear waves is whether they have the bending wave or like what you call it, like the flexure waves. Yeah. So I think that's the difference between them.
I mean, okay. Looks like you are so much confident in explaining my question. I mean, for my question, but actually you are, talking about something totally different. So anyway, no, it's okay. Yeah. So, do you think we are measuring pure shear waves or torsional shear waves? Which one?
Because actually, I watched the live YouTube before I entered this presentation. So I now know that we are using the torsion shear wave, but actually the past time I felt like we're using the pure one.
Okay. All right. Now it's good to know that you do have a correct idea. We are measuring torsional shear waves, right? And then, but the figures, the diagrams, the schematic diagrams you explained today is not related with torsional shear waves at all. It is like a pure shear wave, right? Yeah, so that's why I brought up this question to you. Right, thank you guys. And then again, I appreciate your efforts and time and this late. And then I say very much, I thank you guys very much. And then I hope you can make more contribution to the second project too. Wonderful. Thank you guys. Bye.
Thank you, Professor.
Good evening. Professor.
The second project is the one that they should climb a mountain, right, Professor?
Sorry, again?
The second project, I mean the one that you
Oh yeah, Rocky Mountain hiking.
Maybe you can explain it to Jerika since she doesn't join the
okay.
class.
She was not in the class.
Yes,
actually, in a civil engineering project, and then we like to know the strikes and dips of bedrock outcrops. Okay, so when we are trying to make tunnels or underground spaces or excavations, and then one of the causes to bring some kind of failures in tunneling activities is they do not have an idea what the weakness planes or the discontinuity planes are developed in which direction. So if they knew the direction or orientation of those weaknesses or discontinuities, and then they utilize it to prevent the failure. Okay. And so the first stage of project planning is to look to investigate geological structures. So by doing some kind of aerospace the pictures or kind of the mappings. Mapping means you go to the sites and then take a look at the direction or planes of the bedrock, exposed bedrocks. And then so you have to measure strikes and dips, right? And then the strikes and dips of the bedrock surface, and also if you can see joints or faults out there, and then also you have to map those things too. So those are linear structure, and then bedrock surface is like a planar structures. So we have to be able to map all those anomalies, okay, weakness planes or planes of discontinuities. And so this Friday we are going to talk about stereographic projection for mapping those weaknesses and discontinuities. So once they knew it, And then next week, I am asking students to visit the real Rocky Mountains and to see and to find those exposed bedrocks and try to determine strikes and dips of the bedrocks, and also try to find a joints and then the faults. I'm not sure about that, by the way. And then utilizing the smartphone applications. And smartphone application is telling you like the strikes and dips and then the orientations or sort of things. So they make some travel and then hiking, and then in group, and so they're enjoying the beautiful weather of the year this time. And then so they build up like a friendship between the students, and then so they take a good pictures of it, and then and when they climb down, and then they can enjoy some food and then drinks together. So mostly most of the years the students show very good opinion, the responses on this kind of project, so they can relax themselves and they can enjoy the fresh air and something. Okay. All right, good. And then
Professor, I think the lady
Minjung. Yeah, Minjung is waiting. Okay. Yeah, please
is
ask her
very
to come.
worried. I think she's worried. Oh, should I ask her to come in here?
Yeah, to come. So looks like you graded their presentation too, right? Yeah,
yes, Professor.
Yeah, please
Yes,
share
Professor.
your grading with me too. Okay.
So, on what scale, Professor?
20, the maximum.
Maximum
20.
is
Oh, the
20.
maximum is
20.
It's okay. Yeah, 20. Yeah, please scale to 20.
But I did not grade them individually. I grade them by group.
It's okay. By group, so you gave just the one grade to all of them. Okay.
Actually,
Next time.
I split it like 50% for presentation, 50% for Q&A. That's what I did.
I did for the individual. I put the name
individual is preferred.
because
Sorry, I did it. I will do that next. I'm so confused with their name.
Because I'll write.
Professor. Minjong is not replying, so I don't think she will come.
Yeah, please make a phone call to her.
Hello. Can you come in the Zoom session again? Yeah, yes. Professor is waiting. Okay, thank you. Bye.
If she's coming alone in the meeting.
Sorry, what did you say?
If she's coming alone in the meeting, or maybe.
Oh, I think because she just messaged me about. She said she found out about the sound wave velocity on your presentation, on Professor's presentation. So she wants to clarify about that.
어서 와, 민정아. 아까 내가 발표에 대한 코멘트를 조금 과하게 했지. 미안해. 나도 그런 사람이 아닌데 아까 발표할 때 단어 하나 때문에 좀 마음이 속상했었어. 근데 왜냐면 그 수업 시간에 사운드 웨이브 벨로시티는 틀린 거니까 이거 쓰지 말자라고 하고 아예 제껴놨거든. 그리고 나서 이제 새로운 이론을 우리 저기 프로젝트 하면서 배우자라고 했었잖아. 그래서 이제 그 얘기를 했었는데 사운드 벨라시티가 나오니까 수업을 안 들었네 이제 이런 생각이 들었던 거지. 그래 미안해.
첫 프로젝트라고 적어놨습니다.
내가 뭐 잘못 본 게 있었어? 잘 안 보이네. 그거 저기 공유할래 한번? 공유해 줄래? 공유할 수 있게끔 돼 있어.
연결이 안 됐어가지고요.
저기 마이크가 좀 이상한지 잘 안 들려. 오케이 이제 공유되네. 봅시다. 스토리 했는데 스크린 쉐어링을 스타트 했다고 하는데 화면이 안 바뀌네. 인터넷이 좀 느린가 보다.